Hi dear students, in this session I am going to explain you about crystal field theory. In this crystal field theory, I am going to explain you discovery of crystal field theory, postulates of crystal field theory, d orbital splitting in tetrahedral and octahedral complexes, what is the crystal field stabilizing energy, and what are the high spin and low spin complexes. Coming to discovery of the crystal field theory, in the year 1929, Hans Bethe has discovered this theory. For this theory, Hans Bethe has got Nobel Prize also. So postulates, coming to postulates, he has explained some postulates for this crystal field theory. Those are, when the central metal atom approaches to the ligands, when ligands are approaching the central metal atom will become positive ion, and the ligands, they are coming with the electron pairs, so that they are calling ligands. So when the ligands are approaching central metal atom, ligands behave as negative charge. Ligands are negative charge, central metal atom is positive charge. So between the ligands and central metal atom, there are electrostatic attractions, electrostatic forces. Electrostatic forces are present. Electrostatic interactions are present. When these electrostatic interactions are coming in between these two, then if we can consider it as a crystal, because of these electrostatic forces, a field can be generated in this crystal. So that field is crystal field. So this crystal field theory will explain mostly the interaction between ligands and central metal atom through electrostatic forces. Because of these electrostatic forces, how the d orbital will split, in the central metal atom. Because of this d orbital splitting, how the properties will change in the crystal. Means what? Magnetic properties and colors and electric properties, how all these properties will be changed because of these electrostatic forces and d orbital splitting in the central metal atom. These are the postulates what he has explained in this crystal field theory. Coming to d orbital splitting in the central metal atom, let me explain you. D orbital splitting in central metal atom. Metal so, when the ligands are approaching the central metal atom, based on the number of ligands, this complex are metal ligand. Depends upon the ligand number, this complex will get a structure. That structure can be tetrahedral, octahedral, square planar, and trigonal bipyramidal, etc. But in your syllabus, tetrahedral and octahedral complexes are there. So that I am going to explain you the tetrahedral and octahedral complexes. In this tetrahedral and octahedral complexes, how the d orbital will split into energy levels. So coming to d orbital splitting in tetrahedral and octahedral. Tetrahedral. When the ligand when the four number of ligands approaches central metal atom. Four number of ligands approaches central metal atom means metal, ligand, ligand, ligand and ligand. When four ligands approaches the central metal atom, and that will give square planar or tetrahedral complexes. But here we are studying about tetrahedral complexes. Tetrahedral complex. In tetrahedral complexes, how many ligands are present? Four number of ligands. The coordination number in tetrahedral is 4. Now, ligands are negative charge, central metal atom is positive charge. That thing we know very well. So when ligands are approaching central metal atom, the d orbital present in the central metal atom will split into different energy levels. How that d orbital will split into different energy levels? Let's see. Before going to know about the splitting of d orbital, let's see what are the d orbitals. These 5 are the d orbitals. dxy, dxz, dyz, dx square y square and dz square. If you observe clearly, in this dxy, dxz and dyz orbitals, the lobes or orbitals are arranged or occupied in between the axis. These 3 are in between the axis. And coming to these 2 are along the axis. They are arranged or occupied the place along the axis, on the axis. So these 2 are along the axis, these 3 are between the axis. The key point you have to remember, between the axis. These 3 are between the axis, these 2 are along the axis. Fine. Now if we can take example tetrahedral complexes, how these 5 orbitals will split into energy levels in tetrahedral. Let's check it. D orbitals are 5: dxy, dxz, dyz, dx square y square and dz square. When the ligand approaches, they will get a little high energy than atomic energy because of the forces. And if the ligands will approach closely to this d orbital in tetrahedral, they will split into two energy levels. Those are dxy, dxz and dyz. dxy, dxz and dyz. Remaining 2 are dx square y square and dz square. Why this is happened? Because 2 orbitals will get lower energy, 3 orbitals are getting higher energy. What is it? Why these 3 are getting higher energy? Why these 2 are getting lower energy? Let me explain you. I am taking tetrahedral structure. This is tetrahedral structure. I am taking this tetrahedral structure and keep it into a cube. Keep it into a cube. Keep it into a cube. This is cube. This is axis. These are the axes. X, Y, Z. When tetrahedral structure is there. This is the tetrahedral structure. This is metal atom. Here ligand, ligand, ligand and ligand. To understand clearly, I am taking a cube and I kept this tetrahedral structure into that cube. If we can observe here, these ligands are placed at in between the axis. In between the axis. See, this is axis, this is axis, this is axis, and this one is axis. This is axis. These are the axes. In between the axes, ligands are present in tetrahedral complexes. So when the ligands are present in between the axes, means that ligands are approaching the central metal atom towards dxy, dxz and dyz orbitals. Why? Because in dxy, dxz, dyz orbitals, lobes are arranged in between the axes. In between the axes. So when the ligands are approaching in tetrahedral complexes to the central metal atom, in between the axes arranged orbitals, those are dxy, dxz, dyz, will affect more because of electrostatic interactions than dx square, y square and dz square. Why? These two orbitals are along the axes. So when along the axis orbitals are there, they will not more affected compared to the three orbitals, because ligands are approaching in between the axes. Fine. So now, so that these three orbitals are getting higher energy, these two orbitals are getting lower energy. With how much an amount of energy these three will get higher energy, these two get lower energy. Let's check. This is the average energy, delta tetrahedral average energy it is. And now these three are affected by these two will be affected by these three. So here I am writing 3 by 5 delta tetrahedral. This is 3 by 5 means 0.6 delta T. This energy gap is 0.6 delta T. This energy gap is between the average to higher. Here 2 are affecting on 3. 2 by 3. Just take opposite. Here we are taking 3 by 5 because all are 5. So here 2 by 5 means 0.4 delta T. 0.4 delta T. 0.4 delta T. So this is splitting. This is because of splitting. This is getting higher energy from average energy with 0.4 delta T. This is getting lower energy with 0.6 delta T. Fine. This is the splitting of d orbital in tetrahedral complexes. Coming to crystal field stabilizing energy formula. For example, here 2 orbitals are there, right? Here 3 orbitals are there. These 3 orbitals are calling as T2G. These 2 are EG orbitals. So in tetrahedral complexes, T2G orbitals are occupied higher energy, EG orbitals are occupying lower energy. Fine. So crystal field stabilizing energy. How this crystal is getting stabilization with some amount of energy. That energy can be calculated by crystal field stabilizing energy. Calculation of CFSE, crystal field stabilizing energy. The formula is electrons present in Eg, electrons present in Eg orbital, electrons present in Eg orbital into multiply with 0.6 delta T, 0.6 delta T, 0.6 delta T minus electrons in T2G orbitals into 0.4 delta T plus pairing energy. This is the formula to find out the crystal field stabilization energy. Fine. So actually, if tetrahedral complexes are there, they can have D1 electronic configuration, D2 electronic configuration, D3 electronic, so on, D9 or D10 electronic configuration. How many electrons are present in D orbital, that many electrons will be filled in Eg and T2G level. Fine. If how many electrons are present in these two orbitals, based on that, by using this formula, we can able to tell the crystal field stabilization energy. Fine. So, once again, this is d orbital in a metal ion, and this is the little bit average energy of d orbital in the sphere, crystal field, spherical field, average energy of d orbital in spherical field, and this is the d orbital splitting in octahedral, tetrahedral complex, in tetrahedral. Fine. Now let's see the d orbital splitting in octahedral complexes. In octahedral complexes, octahedral means octahedral. Hedral means this is hedral. So these shapes will be 8 present in that structure. But it's okay. In octahedral complexes, 6 ligands will be participated in the coordination compound. So around the metal atom, 6 ligands will be there, and that structure will be octahedral structure. If a complex form octahedral structure, how the d orbital will split by those 6 ligands approach, let's see. Let's see. So this is octahedral, metal, ligand, and ligand. 4 number of ligands, 6 number of ligands are there, and those will be form octahedral structure. This is octahedral structure. Now, when these 6 ligands are approach the central metal atom, d orbital will affect to split into 2 energy levels because of electrostatic forces between ligand and metal ion. Ligands are acting as negative charge, metal is acting as positive charge according to crystal field theory. Fine. Now, metal ion in average stage, it is in this stage. When ligands are approached the central metal atom, little bit trying to approach the central metal atom, it will get average energy in the spherical field, in the spherical crystal field. Then d orbitals will get little higher energy compared to metal ion. Now these orbitals will get affected by the electrostatic forces, and d orbital will split into 2 energy levels. Now how the splitting will be? How the splitting will be? How the splitting will be? Let's see. Here ligands are approached along the axis. If you can observe, we can keep this structure into cube also. All ligands are along the axis x, y, z, along the axis. Now these, when ligands are approaches along the axis, whatever the orbitals are along the axis orbitals, they will get affected with high repulsion when compared to between the axis orbitals. In d orbital, along the axis orbitals are dx square y square and dz square. These are along the axis because ligands are approaching along the axis. So along the axis orbitals will get higher energy when compared to other orbitals. They'll get higher energy. The lower energy orbitals will be dx square y square. dxy, dyx, dyz, dxj. Because these orbitals are between alignment of the lobes in these three orbitals. These three orbitals are calling as T2G orbitals, and these two are EG orbitals. Now average energy is this, and this is delta octahedral, and compared to this average energy, these three orbitals will get dxy, dxz, dyz. These three will get lower energy with 2 by 5 delta octahedral or 0.4 delta octahedral. And these two will get higher energy from average energy with 3 by 5. Total are 5 d orbitals. So 3 are affecting these two. So 3 by 5 delta octahedral or 0.6 delta octahedral. Now, what is the crystal field stabilization energy? The formula is crystal field stabilization energy formula for octahedral complexes is electrons in T2G into 0.4 plus electrons in EG into 0.6 plus pairing energy. This is the formula to get crystal field stabilization energy for octahedral complexes. Fine. So octahedral complexes also will be have D1 electronic configuration, D2, D3, D4, D5, D6, D7, D8, D9, D10. So how many electrons are present in d orbital when it's formed crystal? So that many electrons will be filled in these two orbitals. So based on those electronic number, so this formula will give the answer. But here, so this is the basics of tetrahedral and octahedral complexes. These are the tetrahedral octahedral complexes. Now I am going to tell you the high spin and low spin complexes. So I'm going to give a small information by this image. If the ligands, the approaching ligands are strong ligands, or weak ligands. Ligands can be strong or weak. That thing you have to remember, and that series also I will write. So strong field ligands are there, weak field ligands are there. If strong field ligands are approaching the central metal atom, then this energy, this splitting level will be more. If strong ligands are there, this energy will be more because the splitting will be very, very high. The splitting will be very, very high. If weak field ligands are approaches the central metal atom, this energy will be very less. That thing I am going to explain now. That is high spin and low spin complexes.